Today I would like to demonstrate the capabilities of the module for cleaning and calibrating yield maps. Let's start with the user interface and then explore various usage scenarios. The module can be accessed by clicking on the icon to the right of the dataset name. Currently there are 4 launch options available. Automatic processing includes cleaning and calibration, one-click solution with preselected by the algorithm's parameters, cleaning only, calibration only, and combination of cleaning and calibration. Let's delve into the customizable parameters of the module and start with cleaning. The cleaning algorithm allows you to choose the yield attribute for which the cleaning will be performed. By default, the algorithm suggests the most optimal option. There is also an extended configuration, including excluded attributes, those attributes that will not impact the cleaning process. These are necessary in cases where there is an anomaly in the data, for example, a sensor incorrectly recorded humidity at some point, that should not be removed. In addition, you can manually select the range of acceptable values for any attribute. Calibration is implemented in 3 variants. Pathwise calibration, suitable for the cases where multiple machines were used or harvesting was done on different days. It means the equipment had different calibrations, resulting in clear linearity on the map. Calibration by the average total sets the average total value to which the dataset is calibrated, optimal when absolute indicators deviate from the actual values. And conditional calibration allows setting a range of values from minimum to maximum, which the selected dataset attributes should fall, suitable for cases where a sensor failure occurred or minimum-maximum attribute values are known. Let's move on to the real scenarios. Consider the first field. To choose the optimal combination of cleaning and calibration parameters, let's evaluate the field visually based on its main attributes. It's evident that the field is relatively homogeneous, with no distinct zones. Among the attributes, there is also no column corresponding to the machine identifier if there are multiple machines or the day. Additionally, you can see the statistics of the field, and there are anomalies presented in the data represented by red and bright green geometries, which can also be observed in the attribute statistics. Thus, it can be concluded that this field requires only cleaning to remove anomalies. So let's choose cleaning. Let's choose the yield attribute, yield with mass, without any advanced configuration, and just run the process. For efficiency, the operation was performed in advance. Let's examine the result. And let's choose our target attribute, yield with mass. Visually and statistically, it can be concluded that the dataset is now in an optimal state. So let's move on the second field. Again, here we perform a visual inspection of the attributes. The case appears similar to the previous one. Accordingly, we initiate a single cleaning. So let's choose clean only, the same yield attribute with mass without any advanced configuration. Again, as for the previous field, we did this in advance. Let's inspect the result. On the resulting map, it's noticeable that some data without explicit anomalies in the yield with mass attribute has been removed. In this situation, it's necessary to check other attributes for anomalies and assess whether they should be removed. So let's move to more precise comparison here, and what we see that deleted points has no anomaly in this region. Let's inspect the other one. Start with crop ID. And there is only one number, so it can be anomaly. Distance traveled from the previous point. The same situation, no anomalies, dry matter. And here we see the anomalies in the data, likely due to a sensor malfunction. Just remember it for our further operations. Let's examine element ID, and there is no any anomalies. Elevation, the same, only one number. Let's move further. Machine identifier, also without any anomalies. Machine heading. No moisture. And here we see the same anomaly as we see for the dry matter column. Let's remember it's 2. Let's examine vehicle speed. Again, the data is normal. Wet mass as we see previously is also correct. Width of elements, also without any abnormal regions, and yield as volume. Okay. In this case, it's necessary to rerun the cleaning with moisture and dry matter as excluded attributes to eliminate the abnormal values and to not delete it from the resulted map. So let's move to our original dataset. Let's check clean. Proceed with the same yield attribute as mass, and here we should exclude our moisture attribute and dry matter attribute here. We select it, we hide the configuration and run our algorithms. So let's inspect the result. And here we see that our dataset looks pretty good, and now is in optimal state. So let's move further and let's consider a more complex case. The nullity is clearly visible in the dataset, and there is more than one harvesting machine. Let's check it. Indexing to the machine usage map. Here we have different machines that correlates with our wet mass by the nullity. Additionally, there are anomalies, 0 values and too high values, and we select the option for both cleaning and calibration in that case, because we need firstly to remove the anomalies from the dataset and then to calibrate it between the different machines. However, in this scenario, visual assessment reveals that one of the zones significantly differs in the size and values, too high relatively to the entire dataset. Like here we have two different green stripes and values around 20, and the average value of the entire dataset is around 4. So this corresponds to the abnormal values. And if we choose firstly cleaning and then calibration, potentially this point will be removed. So let's start our process. We choose clean and calibrate. Here we have two possible options for the operations. The recommended sequence is cleaning followed by calibration.